Welcome to our channel. Don't forget to like, share, and comment your valuable thoughts. We'd love to hear from you. You can comment your doubt or topic you want video. Chapter 2. Is matter around us pure? Key topics covered. What is a mixture? Types of mixtures. Solutions and their properties. Concentration of solutions. Separation of mixtures. Types of pure substances. Elements and compounds. Question 1. What is a mixture? A mixture is a combination of two or more substances, either elements, compounds, or both, that are physically mixed together but not chemically combined. Examples of mixtures. Air, a mixture of gases like oxygen, nitrogen, carbon dioxide, etc. Salt water. Salt dissolved in water. Soil, a mixture of sand, minerals, organic matter, water, and air. Question 2. What are the types of mixtures? Homogeneous mixture. Definition. A homogeneous mixture is a mixture in which the components are uniformly distributed and appear as a single phase. Key characteristics. Same composition throughout. No visible boundaries between components. Components are mixed at the molecular level. Cannot be separated by physical means easily. Appears as a single substance. Examples. Sugar in water. Sugar is completely dissolved and cannot be seen separately. Air, a uniform mixture of gases like nitrogen, oxygen, CO2, etc. Vinegar, a mixture of acetic acid and water. Alloy, a mixture of metals like brass, zinc plus copper. B. Heterogeneous mixture. Definition. A heterogeneous mixture is a mixture in which the components are not uniformly distributed and can often be seen as separate substances. Key characteristics. Composition is non-uniform. Two or more phases are visible. Components can be easily separated by physical methods. Particles do not mix completely at the molecular level. Can show settling or layering of substances. Examples. Sand in water. Sand settles down and is visible separately. Oil in water. Two different layers are seen. Immiscible. Salad. Individual vegetables are easily distinguishable. Chalk powder in water. Chalk does not dissolve and settles down. Summary table. Type of mixture, uniformity, visibility of components, separation method. Example. Homogeneous, uniform, not visible, difficult. Molecular level. Saltwater, air. Heterogeneous, non-uniform, visible, easy. Filtration, etc. Sand in water, salad. Question 3. What is a solution? Definition. A solution is a homogeneous mixture of two or more substances, where one substance, solute, is dissolved in another, solvent. Components of a solution. Solvent. The component present in the larger amount. It dissolves the solute. Example. Water in salt solution. Solute. The component present in the smaller amount. It gets dissolved in the solvent. Example. Salt in salt solution. Example of a solution. Salt solution equals salt, solute, plus water, solvent. Sugar in water, alcohol in water, and air, gases mixed, are also examples of solutions. Key properties of a solution. Homogeneous. Same composition throughout. Clear and transparent. Light passes through without scattering. No settling of particles. Solute does not settle at the bottom. Cannot be separated by filtration. Solute particles are too small. Stable. No change occurs over time if undisturbed. Particle size. Less than 1 nanometer, very small. Summary table. Property, solution. Type of mixture, homogeneous. Visibility of particles, not visible. Separation method, cannot be filtered. Stability, stable. Particle size less than 1 nanometer. Question 4. What are the types of solutions? Definition, recap. A solution is a homogeneous mixture of two or more substances. Based on the physical state of the solute and solvent, solutions are classified into different types. Let's learn about the types of solutions based on the physical states of the solute and the solvent. 1. Solid in liquid. When a solid is dissolved in a liquid, it forms a homogeneous solution. Example: sugar in water or salt in water. These are common in our daily life and appear as clear, uniform liquids. 2. Gas in gas. This type of solution occurs when one gas is evenly mixed in another gas. Example: air, which is a homogeneous mixture of gases like oxygen, nitrogen, carbon dioxide, and more. 3. Liquid in liquid. When two liquids are mixed and form a single phase, the solution is homogeneous. Example: vinegar, which is acetic acid in water, or alcohol mixed in water. 4. Gas in liquid. A gas can also dissolve in a liquid under pressure to form a homogeneous solution. Example: carbonated drinks like soda, where carbon dioxide is dissolved in water. 5. Solid in solid. Some solids mix together to form solid solutions called alloys. Example: brass, a mixture of copper and zinc. These are uniform throughout and used in tools and construction. 6. Liquid in solid. When a liquid is mixed with a solid, it can form a homogeneous solid solution. Example: dental amalgam, mercury mixed with silver, commonly used in tooth fillings. 7. Gas in solid. Even gases can dissolve in solids to form solid solutions. Example: hydrogen gas absorbed in palladium metal, useful in scientific applications. Note: all these examples are homogeneous solutions, meaning their composition is uniform throughout and particles are not visible to the naked eye. Most common types in daily life: salt in water, solid in liquid, soda water, gas in liquid, or gas in gas, alcohol in water, liquid in liquid, brass, solid in solid. Key points: solutions can be formed in all three states of matter: solid, liquid, and gas. The solvent determines the physical state of the overall solution. Most common solutions in everyday life are liquid solutions. Question 5. What is the concentration of a solution? Definition: concentration of a solution refers to the amount of solute present in a given quantity of solution or solvent. Tells us how strong or weak the solution is. Types of solutions based on concentration. Dilute solution. Contains a small amount of solute and more solvent. Appears lighter or less intense. Example: 1 spoon of salt in 1 glass of water. B. Concentrated solution. Contains a large amount of solute and less solvent. Appears stronger or darker in color. Example: 5 spoons of salt in the same amount of water. C. Saturated solution. A solution in which no more solute can dissolve at a given temperature. Extra solute settles down at the bottom. Fixed maximum solubility. Example: when adding more sugar to tea no longer dissolves. D. Unsaturated solution. A solution in which more solute can still dissolve at that temperature. Not yet at maximum capacity. Let's understand how to calculate the concentration of a solution using a simple formula. Formula: concentration % equals mass of solute / mass of solution times 100. Remember, mass of solution equals mass of solute plus mass of solvent. Example: suppose we dissolve 5 grams of salt in 95 grams of water. Step 1. Mass of solution equals 5 g salt plus 95 g water equals 100 g. Step 2. Now apply the formula. Concentration equals 5/100 times 100 equals 5%. So, the concentration of the salt solution is 5%. This tells us that 5 grams out of every 100 grams of this solution is salt. Understanding this helps in preparing precise solutions in science labs, cooking, and medicine. Let's learn about mass by mass percentage, also written as W by W %. Formula: mass by mass % equals mass of solute / mass of solution times 100. Important: mass of solution equals mass of solute plus mass of solvent. Example: Imagine we dissolve 5 grams of salt in 95 grams of water. Step 1. Total mass of solution equals 5g salt plus 95g water equals 100 grams. Step 2. Now apply the formula. Mass percent equals 5/100 times 100 equals 5%. This means the mass by mass percentage of the salt solution is 5%. In simple words, 5% of the total solution's mass is salt, and the rest is water. This calculation is very useful in chemistry, pharmaceuticals, and food industries. Now let's understand mass by volume percentage, also written as W by V%. Formula. Mass by volume percent equals mass of solute in grams/volume of solution in ml times 100. Remember, mass is measured in grams g. Volume is measured in milliliters SL. Example. Suppose you dissolve 5 grams of sugar in 100 milliliters of solution. Step 1. Apply the formula. Mass/volume percent equals 5/100 times 100 equals 5%. So, the mass by volume percentage of the sugar solution is 5%. This tells us that in every 100 milliliters of the solution, there are 5 grams of sugar. Such calculations are useful in medicine, chemistry labs, and daily kitchen measurements too. Now let's explore the third type of concentration. Volume by volume percentage, also known as V by V%. Formula. Volume by volume percent equals volume of solute in ml/volume of solution in ml times 100. Important. Both solute and solution are measured in milliliters ml. Example. Let's say you mix 25 milliliters of ethanol into a total 100 milliliters of solution. Step 1. Use the formula. Volume percent equals 25/100 times 100 equals 25%. So, the volume by volume percentage of ethanol in the solution is 25%. This means that in every 100 milliliters of this solution, 25 milliliters is ethanol. This type of calculation is commonly used in making perfumes, alcoholic drinks, and lab mixtures. 1. Mass by mass percentage. W/W%. Question 1. 10 grams of sugar is dissolved in 90 grams of water. Find the mass by mass percentage of sugar in the solution. Explanation. Mass of solute equals 10g. Mass of solvent equals 90g. Total mass of solution equals 10 plus 90 equals 100g. Mass percent equals 10 divided by 100 times 100 equals 10%. Question 2. 25 grams of salt is present in 225 grams of solution. What is the mass by mass percent? Solution. 25 divided by 225 times 100 equals 11.11%. 2. Mass by volume percentage, with V%. Question 3. 5 grams of salt is dissolved to form 100 milliliters of solution. Find the mass by volume percentage. Solution. 5 divided by 100 times 100 equals 5%. Question 4. 15 grams of glucose is present in 250 milliliters of solution. What is the mass by volume percent? Solution. 15 divided by 250 times 100 equals 6%. 3. Volume by volume percentage. V/V%. Question 5. 20 milliliters of alcohol is mixed in 100 milliliters of solution. Calculate volume by volume percentage. Solution. 20 divided by 100 times 100 equals 20%. Question 6. 40 milliliters of vinegar is mixed with water to make 200 milliliters of solution. Find the V/V percentage. Solution. 40 divided by 200 times 100 equals 20%. Question 6. What are suspensions and colloids? Suspension. Definition. A suspension is a heterogeneous mixture in which the solute-like particles do not dissolve but remain suspended throughout the bulk of the medium. Key features of suspension: heterogeneous. Composition is not uniform. Visible particles. Particles are large enough to be seen. Particle size greater than 1000 nanometers. Particles settle down. On standing, particles settle due to gravity. Can be filtered. Solute particles can be separated by filtration. Does not show Tyndall effect, in dilute form. Unstable mixture. Needs shaking/stirring before use. Examples: chalk powder in water, muddy water, flour in water, sand in water. B. Colloid. Definition: a colloid is a heterogeneous mixture that appears homogeneous to the naked eye, where the particle size lies between those in true solutions and suspensions. Key features of colloids: appears homogeneous, but is actually heterogeneous. Particle size between 1 nanometer to 1000 nanometers. Particles don't settle. They remain dispersed throughout. Cannot be filtered. Particles pass through filter paper. Shows Tyndall effect, scattering of light. Stable mixture. Doesn't separate on standing. Brownian motion. Particles show random movement. Examples: milk liquid in liquid, fog liquid in gas, smoke solid in gas, shaving cream gas in liquid, butter jelly paints. Tyndall effect. Visible scattering of light by colloidal particles. Beam of torch in fog or dust shows this effect. Let's compare suspension and colloid across various features. Type of mixture. A suspension is a heterogeneous mixture. The components can be seen separately. A colloid appears homogeneous to the naked eye, but is actually heterogeneous at a microscopic level. Particle size. In suspensions, particle size is greater than 1000 nanometers. In colloids, particles range from 1 to 1000 nanometers. Particle visibility. Particles in a suspension are visible without a microscope. Colloidal particles are not visible to the naked eye. Settling of particles. Suspension particles settle down on standing. Colloids are stable. Their particles do not settle. Filtration. Suspensions can be separated by filtration. Colloids cannot be filtered using ordinary filter paper. Tyndall effect. Suspensions generally do not show the Tyndall effect, unless very concentrated. Colloids do show the Tyndall effect. They scatter light. Stability. Suspensions are unstable. Particles settle over time. Colloids are stable. They remain uniformly mixed for a long time. What is a suspension? A suspension is a heterogeneous mixture in which solid particles are dispersed in a liquid or gas but do not dissolve. These particles are visible and can settle down over time. Properties of suspension with examples. 1. Heterogeneous mixture. The composition is not uniform throughout. Different phases can be seen separately. Example: muddy water. You can see water and mud separately when it settles. 2. Particles are visible to naked eye. The solid particles in suspension are large enough to be seen directly. Example: flour in water. You can see the flour particles floating or settling. 3. Particles settle down on standing. On leaving undisturbed, the suspended particles settle at the bottom due to gravity. Example: chalk in water. Chalk powder settles at the bottom after some time. 4. Can be separated by filtration. Since the particles are large, they can be filtered out using a filter paper or strainer. Example: sand in water. Sand can be removed easily by pouring the water through a filter. 5. Opaque or cloudy appearance. Suspensions often look cloudy or opaque because light does not pass through easily. Example: mixture of paint and water. Paint in water looks thick and cloudy. 6. Does not show Tyndall effect usually. Most dilute suspensions do not scatter light, but concentrated ones might show a little scattering. 7. Unstable mixture. Suspension is not stable. It separates into layers over time and needs to be stirred or shaken before use. Example: medicines like antacids need shaking because the solid settles at the bottom of the bottle. Let's look at some real-life examples of suspensions. Mixtures where solid particles are dispersed in a liquid but eventually settle down. Muddy water. In this, mud is the solute and water is the solvent. You'll commonly see this during the rainy season or floods, where soil mixes with rainwater. Chalk in water. Here chalk powder is mixed in water. It's often used in school science experiments to show sedimentation. Flour in water. Wheat flour mixed with water forms a suspension. This is frequently observed while preparing dough or batter in cooking. Sand in water. Sand is the solute and water is the solvent. This example is perfect for demonstrating filtration and sedimentation processes. Antacid syrup. Antacids contain magnesium compounds suspended in water. These syrups are taken for relief from acidity. Paint in water. Water-based paints have paint pigments suspended in water. These are widely used for wall painting. Each of these examples shows how suspensions play an important role in everyday life and practical applications. What is a colloidal solution, colloid? A colloid is a heterogeneous mixture that appears homogeneous to the naked eye, in which microscopic particles of one substance are evenly dispersed in another. The particle size is between a true solution and suspension, 1 to 1000 nanometers. Particles do not settle and cannot be filtered easily. Properties of colloidal solutions, with examples. 1. Heterogeneous mixture, appears homogeneous. Though actually heterogeneous, colloids look uniform to the naked eye. Example: milk. Looks uniform but under a microscope, it contains tiny fat droplets in water. 2. Particles cannot be seen with naked eye. The dispersed particles are too small to be seen individually. Example: fog, tiny water droplets suspended in air, invisible individually. 3. Particles do not settle on standing. Colloidal particles are small enough to remain permanently suspended. Example: shaving cream. The foam remains stable without settling. 4. Cannot be filtered using ordinary filter paper. Colloidal particles are small enough to pass through regular filters, but can be separated using special filters, ultrafiltration. Example: gelatin in water. Cannot be removed by simple filtration. 5. Shows Tyndall Effect. Colloids scatter light, making the light beam visible through the mixture. Example: sunlight through mist/fog. The beam becomes visible due to scattering. 6. Stable mixture. Colloidal solutions are quite stable and do not separate upon standing. Example: blood plasma. Remains stable unless processed. 7. Brownian motion. The colloidal particles show continuous, random zigzag movement due to collisions with molecules of the dispersion medium. Example: seen under microscope in pollen grains in water, observed by Robert Brown. Colloids are special mixtures where tiny particles remain uniformly dispersed without settling. They look homogeneous, but they are actually heterogeneous under the microscope. Let's explore some daily life examples of colloids based on the type of dispersed and dispersion phases. Liquid in liquid. Dispersed phase. Fat droplets. Dispersion medium, water. Example: milk. Found in dairy products and beverages. Solid in liquid. Dispersed phase. Paint pigments. Dispersion medium, water. Example: paint. Used in wall painting and coatings. Gas in liquid. Dispersed phase. Air bubbles. Dispersion medium, water. Example: foam whipped cream. Found in food, cosmetics, shaving cream. Liquid in gas. Dispersed phase. Water droplets. Dispersion medium, air. Example: fog and mist. Common in early morning weather or clouds. Solid in gas. Dispersed phase. Smoke particles. Dispersion medium, air. Example, smoke. Seen in pollution, fire, burning. Solid in liquid. Dispersed phase. Ink particles. Dispersion medium, water. Example, ink. Used in writing and printing. Solid in solid. Dispersed phase. Colored particles. Dispersion medium, glass. Example, colored glass or ruby glass. Used in jewelry and decoration. These colloids are part of our everyday surroundings, from food and weather to paints and perfumes. Their special property. The particles never settle and they often show the Tyndall effect, making them unique and useful in science and life. Let's quickly compare suspensions and colloids, two types of mixtures you often encounter in real life and in science labs. Particle size. Suspensions have larger particles, greater than 1000 nanometers. Colloids have smaller particles, ranging between 1 to 1000 nanometers. Appearance. Suspensions appear clearly heterogeneous. You can often see the separate substances. Colloids may look homogeneous to the naked eye, but they're actually heterogeneous at the microscopic level. Settling of particles. In a suspension, particles settle at the bottom over time. In a colloid, the particles do not settle, remaining dispersed. Filtration. Suspensions can be easily filtered to separate particles. Colloids cannot be filtered easily using ordinary filter paper. Tyndall effect. Suspensions do not show the Tyndall effect. Colloids do show the Tyndall effect. They scatter light. Stability. Suspensions are unstable. Particles separate on standing. Colloids are relatively stable. They remain mixed for long durations. In summary, suspensions are coarser, unstable, and filterable. Colloids are finer, stable, and show light scattering. Understanding this difference helps in many fields, from medicine to food science and chemistry labs. Tyndall effect, explained. Definition. The Tyndall effect is the scattering of light by particles in a colloidal solution, or sometimes fine suspensions, making the light beam visible as it passes through the mixture. Why it happens. The colloidal particles are large enough to scatter and reflect light in all directions. This scattered light reaches your eye, so the path of the light beam becomes visible. Key conditions. Particle size must be between 1 to 1000 nanometers. Mixture must not be a true solution, e.g., salt in water does not show Tyndall effect. Daily life examples of Tyndall effect. Scene description. Sunlight through forest mist, water droplets scatter sunlight. Visible rays appear. Torch through fog or smoke, fog particles scatter the beam. Beam is visible. Laser/torch through milk, milk has colloidal fat. Beam path lights up clearly. Headlights in dusty road, dust scatters the car light beam. Glowing light path. Lab demo. Laser through starch solution, students can clearly see the red beam path inside the beaker. Scientific significance. Helps distinguish between true solutions and colloids. Used in colloid research, detection of fog, dust. Principle used in ultramicroscope for studying particles. Quick concept check. Property Tyndall effect. Seen in colloids. Visibility of light beam, yes. Seen in true solution. No. Particle size 1 to 1000 nanometers. 8. Separation techniques. Explanation chart. Filtration. Method used for insoluble solid from liquid. How it works. Uses filter paper to trap solid particles. Example, sand and water. Evaporation. Method used for solute from a solution. How it works. Liquid evaporates, leaving the dissolved solid behind. Example, salt from salt water. Centrifugation. Method used for particles of different densities. How it works. Rapid spinning separates heavier and lighter components. Example, cream from milk. Sublimation. Method used for sublimable solids from non-sublimable solids. How it works. Sublimable solids change directly from solid to gas. Example: camphor or iodine from sand. Chromatography. Method used for components of dyes, pigments. How it works. Components travel at different speeds on filter paper or column. Example: separate ink colors in black pen. Distillation. Method used for two miscible liquids with different boiling points. How it works. Liquid with lower boiling point evaporates first. Example: alcohol and water. Separating funnel. Method used for immiscible liquids don't mix. How it works. Liquid layers separate due to density differences. Example: oil and water. Crystallization. Method used for purifying solid compounds. How it works. A pure solid crystallizes from a hot saturated solution as it cools. Example: crystals of copper sulfate from impure mix. Short classroom activity idea. Title: Mini Separation Lab. Step activity tools needed. 1. Filter sand from muddy water beaker, filter paper. 2. Evaporate salt water to get salt dish, stove/sun. 3. Sublime camphor from a mixture watch glass, heating setup. 4. Separate cream using centrifuge hand spinner or lab centrifuge. 5. Chromatography with ink filter paper, black pen, water. Fill in the blank quiz. Is used to separate cream from milk. The process of separating dye components is called camphor is separated from a mixture using salt can be obtained from seawater using a separating funnel works for liquids like oil and water. Answers: centrifugation, chromatography, sublimation, evaporation, immiscible. CQ practice. Q1. Which of the following is best suited to separate alcohol from water? Filtration. B. Distillation. C. Chromatography. D. Crystallization. Correct. B. Distillation. Q2. Which technique is based on different solubilities in a solvent? Sublimation. B. Evaporation. C. Chromatography. D. Filtration. Correct. C. Chromatography. 9. Types of pure substances. Pure substances consist of only one type of particle, atoms or molecules, and have uniform composition. They are classified into A. Elements. Feature description. Composition made up of only one type of atom. Simplification cannot be broken into simpler substances by chemical or physical methods. Properties: unique physical and chemical properties. Type examples: metals, non-metals, metalloids. Examples of elements: oxygen, O2. Non-metal, essential for respiration. Iron, Fe. Metal, used in construction. Carbon, C. Non-metal, basis of life. Gold, U. Metal, used in jewelry. B. Compounds. Feature description. Composition made up of two or more elements chemically combined. Ratio elements are always present in a fixed ratio. Separation can be broken into elements only by chemical methods. Properties different from the elements that form them. Examples of compounds: water, H2O. 2 hydrogen plus 1 oxygen. Carbon dioxide, CO2. 1 carbon plus 2 oxygen. Sodium chloride, NaCl. Table salt. Methane, 4. Fuel gas. Comparison table. Property: element, compound. Made of one type of atom, two or more atoms of different elements. Breakable. No, yes, chemically. Ratio not applicable, fixed ratio of elements. Example: FeO2, CH2O2, NaCl. Quick check, fill in the blanks. A compound is formed by the combination of elements. An element is made up of only one type of water is while oxygen is an can be broken chemically, but not. Answers. Chemical, atom. Compound, element. Compounds, elements. MCQ for practice. Q1. Which of the following is an element? Water. B. Carbon dioxide. C. Iron. D. Salt. Answer C. Iron. Q2. In which form are elements combined in compounds? A. Physical. B. Random. C. Fixed chemical ratio. D. Equal weight. Answer C. Fixed chemical ratio.